I'll take it. Perfect. All right, did everyone get kind of a packet of papers? Yeah? All right. These papers are the next unit. We're going to get into that today, so you can go ahead and pop this in your binder if you want to. We're first going to wrap up our unit circle, though, before we get into the next unit. Also, can you do me a favor? I forgot to tell you guys. Can you go ahead and grab a calculator on my door over there? We're going to get to that today, too. If you don't have your own, go ahead and grab one of mine. No. It's just hot. Hotness coming in. All right, so we're going to get into trig today. We didn't start this, right? Nothing? Okay. So, last year for a good solid probably 3 or 4 months, perhaps, you guys were talking about trig, and a lot of that involved around this unit circle. Pretty important idea. What we're going to do is fill out the unit circle and talk about some of the problems at the bottom of the page, how we can use the unit circle to answer some questions. I'm just curious though, what do we remember about the unit circle? Are there any particular points or locations that are familiar? Notice though how you see those black lines on there? Okay, those are typically where you would write the degree location, but we are not going to talk about degrees this year. It's all radians, those little pi numbers. Okay, we'll get used to them, but no degrees this year. All right. So what do we want to try to tackle first? We want to try to tackle the points. We want to try to tackle the radian values. Do we know anything just as a starting place? Want to do the points? Okay. Do we know a point? 1, 0. Perfect.
Top is 0, 1.
Yay, we're on a roll.
The far left is -1, 0.
Uh-huh.
And the bottom middle is 0, -1.
Boom. Good. All right. It's called a unit circle because you're only going out 1 unit from the origin, aka the middle. Okay, so all of those are all ones somehow. So now that those are filled out, the other points are where it gets a little tricky. Do we remember any points or what they involve? What they might look like? There's square roots of 3 over 2, half. Do you remember where that one is?
Is that the first? Is the first one or the third one?
It's this one. Okay.
And then the second one is square root 2 over 2. For both.
For both. Perfect.
And then the third one is half, square root of 2.
Wonderful. Okay, I'm using the little bar as a fraction bar. Okay, just so it's easier for me to write it, but those are all fraction bars. Good. Okay, so I'm going to tell you right now, we have to know this first quadrant, everything about it. Okay, eventually the radians and the points. We have to know the first quadrant. We will also have to know the top point, the left point, and the bottom. We have to know those. Okay, the other ones, not so much. Okay, but definitely these ones. We're going to go over all of them now. Okay, so now that we know the first quadrant, can we somehow use these and some patterns to fill out the other ones? Because we're going to be using these same numbers over and over and over again. Do we know any symmetry or patterns we might be able to use? Okay, oh good. So if we're in the second quadrant, all the x's are negative. I like that.
You can like follow the lines, like draw the lines down.
Okay, opposite. Okay, so for instance, if you were to take this first point in the first quadrant and follow that line through the origin to the other side, that same point would show up right there. And you can continue to follow the lines. Alright, so that's one pattern you could use to fill out the third quadrant. If we're in the third quadrant, what about any negatives? Good, Cameron? The y's are definitely negative. What about the x's? They're negative as well. Yep. Okay. What about any type of pattern or symmetry to fill out the other two quadrants?
The middle point, so square root of 2 over 2.
Mm-hmm. Fold it, right. If you were to take this first quadrant and fold it over that way, okay, across the y-axis, this point would land here. So we could write that same ordered pair. And then this point would land here. Okay, we can do some more folding. Just instead of going across the y-axis, we could fold it across the x. So this point would land here. And then the top point would land here. Excuse me. Thank you. All right, so we already said in the second quadrant the x's were negative. What about any negatives in the fourth quadrant? The y's. Good. Are we okay with those points? Notice how you have to know the first quadrant and getting the rest using some patterns not too bad? Okay. Let's go ahead and tackle some radians, some angle measurements with pies. Do we know any radian measures throughout the unit circle? Oh, good, David.
Pi over 3.
Where's
where like the 1/2 and square root of 0 to 2 point is.
Perfect. There's one of them. Again, I'm using the bar as a fraction bar. Good.
The
Jared.
first line on the bottom row is not that one.
Not this one?
Yeah, the one on top of that.
Right, this one.
Yeah.
Yeah, what is that?
Pi over 6.
Pi over 6. Good. Good, David.
The top one is 0, 1 is pi over 2.
Pi over 2. Good. Cameron, do you have a different one?
The one between pi over 3 and pi over 6 is pi over 4.
Awesome. I'm surprised you guys are skipping over the easiest one. Good. Carter?
0 or 2 pi.
0 or 2 pi. Good. I'm impressed. Gotta say it. What about any of the other ones? Okay, so those ones we definitely have to know, right? Are there more, Jarrett? Go ahead.
-1, 0.
Uh-huh. Good. Keep going, Jarrett.
0, -1 is 3 pi over 2.
Awesome. So it looks like you guys already have the big ones tackled, right? You guys figured out the first quadrant and then the other points? That's good. What about the other ones? That's when it gets a little tricky, right? Okay. What we're going to do is we're going to use the ones in the first quadrant that we already know and a simple, a simple counting method to continue through. So notice how if we start at 0 and we first go to pi over 6, that's the same as a 1/6, we'll say arc or degree measurement. If we were to go another 1/6, that would land us here, aka 2/6. But does 2/6 simplify? To 1/3, right? And notice how we have a 1 pi over 3. So we already know that's good. If we go another 1/6, that would land us at 3/6, right? Because we went 3 sections. But 3 over 6 simplifies to 1/2. If we were to go another 1/6, that would be 4 over 6, but that simplifies to what? 4 over 6? Two-thirds, right? So this point would be 2 pi over 3. Okay, we have that 2/3 with a pi. If we were to go another 1/6, we would be at 5 pi because we went 5 sections, but 5 pi over 6 doesn't simplify. So we'll keep it. And if we were to go another 1/6, we'd be at 6 pi over 6. But 6 over 6 is just 1. And notice how we just have 1 pi. So if we keep going, we would be at 7/6. Okay, that doesn't simplify. Next, we would have 8/6, but that's 4 pi over 3. Next, we'd have 9/6, but notice how that's 3 over 2. Next, we'd have 10/6, which would simplify to 5 pi over 3. Another one would be 11/6, but that doesn't simplify. And our last section would be 12/6, but notice how that's just 2. Do you see how we just keep counting all the way around? Okay, so that's good, but we still have some other little pieces here we don't know. And notice how those are the middle points in the quadrants. So we're going to use this pi over 4 to help us out to find those. So if we go pi over 4, that's one section. If we go another pi over 4, that would be 2 sections out of the 4. But notice how 2 over 4 is the same as a half. If we go another section, that would be 3 out of the 4. So that's 3 pi over 4. Another section would be 4 pi over 4, but that's the same as 1. Another section, we would have 5 pi over 4. That doesn't simplify. Another section, we've had 6 pi over 4, but that's the same as 3 over 2, so we're good there. Another section, we'd have 7 pi over 4. That doesn't simplify. And our last section would be 8 pi over 4, but notice how that's just 2. So it works all the way around. Okay, so we just use a counting method. Looks like, though, you guys were already good with the first quadrant, so that's perfect. But notice how you can use those to help you get the rest. We doing okay? All right. So now that we have the unit circle filled out, let's go ahead and relate it to some trig functions. In terms of these ordered pairs, do you guys remember which one represented which trig function, like sine, cosine, tangent? What does the x number represent? What does the y number represent? What do you think, Zane?
X represents cosine.
It does, yep. And the y value?
Sine.
Sine, perfect. So sine and cosine, those are 2 big trig functions. The third one is tangent. How is tangent related to cosine and sine? What's the relationship? Sine divided by cosine. Good. All right, so those are some big ones there. Okay, so in the first quadrant, in terms of trig functions like sine, cosine, and tangent, let's figure out what is positive and what is negative. If you look at these ordered pairs, notice how all the x values are positive. So that must mean the cosine value is positive in that quadrant. So we'll just label that with a C. The y values are also positive, so that must mean sine is positive in that quadrant. Now tangent can be a little tricky because you have to do some division, but if you were to take a positive sine value divided by a positive cosine value, positive divided by positive would give you a positive, so tangent's positive as well. So actually all three trig functions are positive in the first quadrant. We don't have any negative ones. What about in the second quadrant? Can we identify positive and negative? Sine is positive. Notice how all the y values are positive. Good, Zane?
Cosine is negative.
Cosine's negative.
So therefore it's negative.
There we go. All right, so if you took positive sine divided by negative cosine, that would be a negative, so tangent's negative. Okay. What about the third quadrant? Okay, Cameron?
Tangent is positive.
Okay.
And then cosine is also negative.
Cosine and sine are negative. Perfect. And the fourth quadrant. Good, Jared?
Cosine's positive and negative is sine.
Sine and tangent. Perfect. How are we doing? Okay? Alright, so now that we have the unit circle filled out, we're going to use it to help us answer some of these questions at the bottom. So, the first one says sine of pi over 3. Now, whenever you're dealing with typical trig functions like sine, cosine, and tangent, we're going to talk about what these different pieces represent. So for regular trig functions, whatever's inside that parenthesis value is representing some type of angle, okay, or theta is usually the variable we use. Okay, so some type of angle measurement. And your answer is coming from the point on that unit circle. So for instance, for number 1, what we have to do, what this question is asking us to do, is we need to go to the pi over 3 location on the unit circle and figure out the sine value from the point. So let's go ahead and find pi over 3 on our unit circle. I think David found that for us before, somewhere up here. So based off of that point, what is the sine value? Go, Cameron?
Square root of 3 over 2.
Yep, we got that y value right there. So square root of 3 over 2. All right. Number 2 is very similar. We're going to go to the 5 pi over 3 spot on the unit circle and figure out the cosine value from the point. Can you guys find that? Good, David?
1/2.
1/2. Okay. We're looking at this fourth quadrant point right there. All right. Now, tangent can be a little tricky because we already know the point value is cosine and sine. We have to do a little division for tangent. But we're going to go to the pi over 2 spot on the unit circle, and we have to take the sine value divided by the cosine. So take a look at that pi over 2 spot. If we took the sine value divided by the cosine, what would 1 over 0 be? Good, Zane? Undefined. Perfect. Alright, so those are typical trig functions, sine, cosine, tangent. The other ones, 4, 5, and 6, are a little different, because notice how these say arc sine, or you have that little -1 there. Do we remember what that wording or symbol is signifying? What it means? What do you think, Zane?
It's a reciprocal, right?
Not quite. It's inverse. I know what you mean, but it's an inverse, okay? So what this is telling us, okay, arc and the little -1 both mean inverse. For inverses, these ideas switch. So now what's inside the parentheses is representing a point value, whereas your answer should be representing an angle, location, or measurement. Okay, it switches. So for number 4, on the unit circle, we got to figure out where does sine have a value of a half. So take a look at your unit circle. Where do we have a sine, aka a y value of a half? Can we find a particular radian or angle measurement? Pi over 6, definitely. Okay, somewhere right here. Is there another one? Go ahead, Cameron. 5 pi over 6, yep, somewhere over there too. So we actually have 2 answers or 2 locations in this case. We got to be careful with that. All right, check out number 5. So where on the unit circle does cosine have a value of negative square root of 3 over 2? We're looking for the angle or radian measure. Can we find the spot or spots? Go, Cameron.
7 pi over 6.
Okay. So that's right here. Good. Another one, Cameron?
And 5 pi over 6.
And 5 pi over 6. Good. Perfect. All right, last but not least. Tangent, again, a little tricky because you have division going on. So we got to figure out where on the unit circle does tangent have a value of 1. Now remember, tangent, you're dividing sine and cosine. So if you're looking for an answer of 1, we got to figure out where is sine and cosine the same. Because when you divide the same number together, you get 1. Can we be a little tricky or strategic and find those points or locations? Where if you took the y value divided by the x value, you get 1? Zero pi and 2 pi. Okay, so if you took the sine value divided by the cosine, that would be 0. It's okay. We're looking for an answer of 1. What do you think, Cameron? Pi over 4. Notice how if we took this y value divided by that x value, they're the same number, so it would simplify to 1. So we got pi over 4. Is there another spot where they're exactly the same? Go, Jared. 5 pi over 4. Yep, they're both negative. But remember, a negative divided by negative is still a positive. All right. How are we doing with the unit circle? Pretty good? All right. We're going to go ahead and start our first unit. All right, so if you take a look at the cover page I just gave you today, this is kind of the breakdown for how the first unit's going to look. It's a little bit more involved than the unit 0 we just covered because we're going to spend more time on this. But in the first column, you have kind of my breakdown of how long I think each section's going to take. Like I said before, this might change. Okay, we might need more or less time depending on the case, but that's my breakdown. You can anticipate when a quiz or exam might pop up, so you can plan for the future. And then in the last column, it tells you what page numbers that we'll be working on, okay, as well as the homework, okay? So for this first unit, we're going to talk about limits. I know I did with my kids last year a little bit of limits, not sure if we remember or not, but this is going to put us all on the same kind of base page, okay? So let's go ahead and take a look at our first one. The equation of the function to the right is given, and the coordinates of the hole in the graph are -3 and 7/6. Do we remember the name of this type of function when we did all those graphs last week? Do you remember what this type was called? Good, Sierra? Rational, perfect. Okay, so rational functions are always fractions. Notice how that makes sense because the equation is a fraction. Let's go ahead and tackle or kind of rewrite this equation. Can we do some factoring perhaps we'll give it a shot. Can we factor the top and factor the bottom? Some of them might be, the top or bottom might be easier than the other for you, not sure. Give it a try. What do you think, David?
Would the bottom be x plus 3 and x minus 3?
Uh-huh. Difference of squares, good. Top one's a little tricky. That 2 is kind of throwing things off or for a loop. Any takers? Do we need a review to how to factor the top? Go ahead.
2x minus 1x plus 3.
How'd you get that? Good.
Because positive 3 and 2 make 5. Make 6 and minus 1 of x equals 5.
3, 5. Okay. So you did like a little kind of number game in your head to figure it out? That's fine. Okay. I know, right? Okay. I know it is. I don't know if you guys remember, or this is how I typically factor it. I take the first number and the last number and multiply them together. Do you know that trick? ACB, yeah. So if you did the first number times the last number, you'd get -6. And we're going to do a little number game like Justin, right? Like Justin did. We got to think of two numbers that multiply to -6, but add to that 5. Can you think of two numbers that do that? Multiply to -6, add to +5. Okay, so 6 is a little tricky one because 3 and 2, those both multiply to +6, but they add to +5. We need to multiply to -6. What do you think, Jarrett? 6. Okay, so +6. -1. There we go. So, like I said before, this 2 is kind of throwing things for a loop. If you were to divide those two numbers by 2, notice how 6 over 2 would simplify to 3, but this 1/2 doesn't simplify, so you can kind of kick that 2 as a coefficient in front of that x, and there's your other factor. Okay, notice how you get the same thing Justin did. Okay, so if this is how the fraction factors, do you notice anything nice about the way that looks now? Can we simplify it? Do you see anything that might happen?
Cross out the x plus 3.
There we go. And if something crosses out from the bottom and the top, what's happening graphically? It's a whole. All right, so if you take a look at the bottom, notice how x values that wouldn't work would be -3 from the first factor and +3 from the second, because those would make the factors 0. If the x plus 3 cancels out, that's what's making the -3 the whole. And if x minus 3 doesn't cancel out, that's your asymptote. Does that make sense with the graph they gave us? Sure is checking out. All right, so if those cancel out, we're left with a 2x minus 1 and an x minus 3. Just for a little fun, okay, let's go ahead and take that -3 whole value we found, and we'll plug it into this simplified equation. Can you do that? We get -7 over -6. Negative divided by negative is a positive. Have we seen that 7/6 value before? What is that? Do you see that somewhere else up here? It's the y value from the whole, right? So if you take the x value of the whole and plug it into the simplified version, that should give you the y value of the whole. Doesn't that make sense? You plug in an x, you get out a y, right? Y value of whole. Perfect. Okay. Let's see. We can maybe label some things on here. Notice how we have a vertical asymptote at the x value of 3. We said that made sense from the whole canceling and not canceling idea. We also have a horizontal asymptote at the y value of 2. Where do you think that horizontal asymptote of 2 is coming from? Can you look at your equation? Maybe make a guess. Why is this specifically at 2 and not at like 8 or 10? It is the 2 in front of the x. Actually, more specifically, if you were to take this number divided by that number, which we know is 1, right? If you took that number divided by that number, that would give you the horizontal asymptote. Perfect. Okay, we'll get into that more in this chapter, but that's a good tidbit. Okay, so let's go ahead and talk about some of this limit or calculus stuff here. On the left-hand side, we have some pre-calculus statements, things you may have seen last year, but we're going to take these verbal statements and write out what it would look like mathematically. So if we take a look at this, as x approaches, that's what the arrow means, as x approaches negative infinity, the graph of f of x approaches what? So as the x values get really, really negative, meaning as you travel really far to the left, what is the graph approaching? If you were to continue to trace this, what are you getting closer and closer and closer to? What do you think, Cameron? That's what the x's are getting closer and closer to. But what is the graph, aka y value, getting closer and closer to? Go, Jody. It is the asymptote. Yep, it's that y value of 2. Remember, f of x and y mean the same thing, right? So as x approaches negative infinity, the y is approaching 2, the height of the graph. Okay. Now, in terms of calculus, we have a particular way we represent this idea, and we use the little abbreviation lim for limit. Limit is just the idea of getting close to something. Okay, you're approaching your limit, what you're getting closer and closer to. So we say the limit, and then underneath that we write x approaching negative infinity in this case. And then after limit, we write f of x. So the limit, as x approaches negative infinity, of this particular graph is 2. That's what you're approaching. That's what you're getting closer to. Okay, so that's the notation for just this statement. We're going to see what the other ones look like. All right, so as x approaches positive infinity, so as you travel really far to the right, what is your graph approaching? If you were to continue, what would you get really close to? 2 again, yep. Again, we're looking for the y value, aka the height of your graph. Okay, let's take a look at the next one. Oh wait, let's do our notation. Limit as x approaches positive infinity of the f of x graph is 2. All right. As x approaches -3 from the left, the graph is approaching what height, aka y value. So let's go ahead and find where the x value of -3 is. Okay, that's somewhere right here. And if you were to trace the graph from the left-hand side to that point, what are you getting closer and closer to? What's the y value getting closer and closer to? Let's see, as you trace from the left, aren't you getting closer and closer to that hole? Right? So what's the y value of that hole? Go, Justin?
7/6.
7/6, right. So the limit as x approaches -3, just out of curiosity, how might we denote the meaning from the left? Curious if we remember. Okay, so x approaches -3 from the left. We're going to put a little minus sign in the exponent spot. -3 from the left of the f function or graph is 7/6. Okay, let's check out the next one. As x approaches -3 from the right, so there's that -3 value. As we trace the graph from the right, what are we getting closer and closer and closer to? What y value? Good, Zane? The 7/6 again, yep. So limit as x approaches -3, how might we symbolize the right-hand side? Good, David? A little plus, yep, in the exponent spot, good. Equals 7/6, okay. We doing okay so far? Yeah? All right, last two. As x approaches 3 from the left. So let's go ahead and find our 3 mark. Okay, that's somewhere right here. As we trace the graph from the left, what is the height of the graph approaching, aka y value? As you come in from the left-hand side, what's happening to your height? Are you getting closer to something like this point? What's happening as you come in from the left-hand side? Can you describe it? Are you approaching a point like we were before? Not necessarily, right? So if we're not approaching a point, we're either traveling up or down. Which way are we going in this case? We're going down forever. So what are we getting closer to if we keep going down forever? Negative infinity. That's the height of the graph. Your graph's going down forever. All right, so limit or calculus notation, the limit as x approaches 3 from the left, so we need that little minus sign, of the f function is negative infinity. All right, last but not least, as we approach 3 from the right, what's the graph doing? So here's that 3 mark again. As we trace the graph on the right-hand side, notice how our graph goes up forever. So what is the y value or height approaching? Positive infinity, good. All right, so notation, limit, x approaches 3 from the right of the f equation is positive infinity. Perfect. All right, so as kind of a definition, if you want to, the limit as x approaches a number of a function, this represents the y value a graph approaches. Okay, we're always looking for a height, the y value. We doing okay? All right, so we just took a look at some limits in terms of a graph. If you flip the page, okay, we're going to take a look at how we can find some limits if we don't have a graph. Now, I'm being nice because this is the same equation we've just been looking at. So we already know what the graph looks like, and it's actually at the bottom of your page. But I want to go ahead and use a calculator to see what that can do for us as well. So let's go ahead and turn on our calculator. And what I want you to do is to type in this equation into your y equals spot. If there's anything in there right now, go ahead and clear it out. You also have to be careful with fractions to put the whole top and the whole bottom in parentheses. Can we type in our function? Okay. What we're going to do is we're going to let the calculator fill in this table of values for us. So instead of us taking the time-consuming process of plugging in each one of these x values individually, okay, we're going to let the calculator do the work. Now what I want you to do is we're going to select that table set option. Do you see how that's blue? That means you have to hit the blue button first. So we're going to hit second and then window. And the main thing I need you to make sure it's going on this screen is that the independent option is set to ask. Okay, so if it's not, you can use your arrow buttons to scroll over and select ask. What this is doing is we're going to change the fact that we can type in numbers for our calculator to analyze instead of the calculator automatically choosing those numbers for us. Okay, so once that's set to ask, we're going to go now to the table option. You see how that's blue too? You have to hit the blue button again. So table set sets the information, whereas table actually brings up the table. If you have numbers going on in here, you can hit the delete button to get rid of them. Okay, we're going to clear those out so we're starting fresh. We doing okay? So what I want you to do is type in your first x value, that's negative 1,000. Boom, there's our answer if we were to plug it in. Our next one was negative 500. Boom, there's our answer if we were to plug it in. Do you see how quick this is? Instead of taking the time to do it one step at a time. So as you go through the tables or the numbers, I want you to write down the y value answers on your paper. Can we get those numbers? All right, so remember, we're pretending that we don't have a graph in this case. Okay, all we have is an equation. So let's see if we can use this information to help us evaluate a limit. As the x's get very, very, very small, okay, very, very, very negative, what is this equation getting closer and closer and closer to? Remember, we're looking for the y values. So as your x's get really, really negative, meaning we're traveling to the left, what's happening to the y values as you travel to the left? What are they getting closer to? 2. So there's the value of our limit. No graph needed. Okay, we just use the table capabilities on our calculator. What about the other one? The limit as we approach positive infinity. So our x's are getting very, very, very big. What are the y values doing? What are they approaching? 2 as well, okay? And graphically this makes sense because we found those same answers on the previous page, okay? Here's that graph again. Notice how as we trace it really far to the left, we're going to level off. And as we trace it to the right, we're going to level off. All right? So we'll pick up with that last question tomorrow and we'll do another table example as well.